Thank you for your invitation. I just would like a bit to apologize for specialists because I'm working mainly in physics, so it will be a bit different from all the other topics you had today. And I will try to adapt a little my talk to you. Just take this talk more as just for curiosity, I would say, and try to get a few of the ideas we are doing. So the title of my talk today is Single Goal Nano-bipyramids as a spectroscopic platform for applications such as sensing and antennas. This is a work which has been done by three main PhD students, which are the three first people, Ms. Nungbu, Mr. Rai, and Mr. Jose, with many colleagues from physicists also to chemists, and in different labs, either in the University of France, but also related to Vietnam Consortium. And we have been funded by French national province. So the goal of my today talk is how we can use a nanoparticle and to use it as I would say a new platform to be used for spectroscopic applications. And mostly it's a bit different also from the other talk, because what we are interested in is about either of course the physical properties, but also to do this kind of sensing, but not in average, but at the single nanoparticle level. So this is a bit different. So just to give you what we are doing in my team, we are doing things related to optics and especially to nanophotonics. We are using Plasmonics. I will define what it is. It's the optical properties of metallic nano objects. And we are interested in this field as many ways. About nanoparticles, like the bipyramids you have here on the first image, which I will talk a lot today. But we are also interested inside what is happening with a surface, a flat, for example, flat gold surface, which has been, for example, made with holes to induce, let's say, surface waves and to try to manipulate surface waves in order to concentrate the light. And after that, we can use this light to enhance or inhibit some processes. And we are also interested in coupled systems, like two bipyramids in interaction, to see how it's working and this kind of stuff. The second part of our work is related to fluorescence. We have just seen it in a few talks previously. Either from quantum dots or single molecules. And we're interested more in the physical properties like lifetime or spectroscopic to understand if to help, for example, some colleagues in chemistry who are synthesizing this kind of objects to see if it has better quantum yield and to understand why these probes can be better or not. And the last, which is why we are doing all this work, is to couple the two. To couple at the same time a nanoparticle, called nanoparticle, for example, with the molecules, in order to manipulate the fluorescence, for example, to control the direction or to enhance the emission, either the quantum yield or to reduce the lifetime or increase the lifetime as we want, and this kind of stuff. So the content of my work, my talk today, will be in four parts. Maybe I will be briefly about the last part, which is not really your concern, but I will just discuss what we can do. So we'll explain what is Plasmonics, because we didn't talk about it today. So we'll try for you to have the basic ideas of what it is and why it is interesting for sensing applications. After that, I will introduce our objects, or to the objects, which are gold nano-bipyramids, which is our specific properties and why it's very interesting for that. And the two last parts will be about applications. Mostly I will talk about sensing, but briefly also about photonics. So let's begin now. So what is plasmonics? So plasmonics is properties of a metallic or nano object. It can be a surface or a nanoparticle when you shine it with light. So you can have many interactions. Here I just explain you a few very interesting applications. First of all, if you take, for example, a gold nanoparticle like this, a few 10 to 100 nanometer, when you shine it with light, with a specific color, with a specific wavelength, you can have a strong absorption of the light around the particle. And here you see that the light can be concentrated around the nanoparticle. It creates what we call the hotspot, and you can increase locally the light by a factor 10 with a single nanoparticle. If you take two particles interacting to each other, you can increase this up to 1000. So this is really interesting as a nano absorber, and to stock the light, concentrate the light in very, very small part. One of the interesting applications, you have the same properties when you take a surface. You can have a hotspot, not really hotspot, but you can have a concentration of the light near the surface. I will talk about it a bit later. It's called the surface plasmon resonance. And you can use it to increase or to modify the properties of molecules. For example, here, if you take a single molecules, it can be I don't know, rhodamine or a single quantum dots, to place it at a very short distance from this mirror, and you can increase the emission, but you can at the same time also control where the light is going. So this is really interesting for applications, because if you want to collect the light and to see something, it's really important. Another application you can use is to use, for example, grating. A grating is something like this. You can have a periodic pattern. And if you take a gold grating and you put some same molecule near this grating, you can redirect the light in different directions according to the grating period. So this is one way to control also where you can extract light. And some applications, you can also combine the two. For example, you can create an antenna, which is linked, which is when you take, for example, a gold nanoparticle and you bring it near a gold surface. In this case, it's a cube, a silver cube. You put it near a gold layer. And in red here are some molecules, fluorescent molecules. And when the molecules are located in between the nanocube of silver and the gold surface, but you can also achieve a very strong direction of the emission and an increase. So these are some examples of this. Of course, the metals can also, the metallic nano object you use can also be used for electric excitation. So it can be used, for example, if you want to do electrochemistry with this kind of object. It's really possible. So just to go a little bit inside what is really a surface plasmon, we'll just explain you what it is. So the first one I want to discuss about the propagating one. So you take, for example, a flat gold or silver surface. Generally, you need to have a noble metal. It can work with other metals like copper or aluminum if you want. And this surface wave, what are its properties? It can propagate along the surface for distances up to a few 10 of microns. So this is quite interesting because it's quite far from optics. So you can really achieve quite some propagation. In vertical, in the Z direction, you see the order of magnitude is strongly reduced, is around 100 nanometers. So you have in fact a confinement of the light in the vertical direction, and the light propagates along the surface. One way to probe this this model is to do what we call the dispersion. So we just show you the example, rather than to explain the physical properties. The idea is the following: you put this flat gold surface onto a prism like this, and when you shine with white lamp this surface and you look in reflection, What you can see is you have here on the right some experimental data we obtained. You see that for specific wavelengths, there is an absorption at a specific angle. So this is directly what we call the dispersion. It shows that there is a relationship between the angle of the excitation and the wavelength of absorption. The link between the two is called the velocity. So here it's how you can probe. You can see that this mode is existing. So the way to excite the surface plasmon is to select the good wavelength and the good angles to excite it. And when you do that, the light is absorbed onto the surface and you launch this surface. So this is the first one. The other one, which maybe you are more aware about, is the plasmon of a nanoparticle. If you take the gold nanoparticle I showed you before, it's symbolized here, and you shine it with a light. For example, you take this particle in a solution, you shine it with a light, so here you have the light, and when you excite it, in fact, the electron of the particle will oscillate. And with a specific wavelength, you can have what we call a resonance. And it means that you are here a spectrum. You have a maximum of the absorption at a specific wavelength. And at this position, the light is absorbed into the particle. And you have this. What is interesting in the case of gold nanoparticle, for example, is this case. If you take, for example, not a round nanoparticle, not a sphere, but you take a nanorod like this, something anisotropic, what you can exactly control is the position of this resonance. So you have oscillations of the electrons inside the longitudinal along the main axis. And depending on the size of this main axis, you can change the wavelength of the absorption. Here you have an example of some chemical realization. So you directly see, if you take a bottle of this solution of this nanoparticle, but you can see by controlling the size, you control the color. So this is what is a plasma. But what is interesting in the talk today is about the sensitivity due to the local environment. So here I gave you two examples of the two plasmons we just showed. So propagating onto a flat surface. And if you deposit, for example, onto this gold surface, you deposit a very thin layer of another material. Here I show you what we did. It's titanium dioxide, and it's something else. What you can see is here I show you data about on the left, let's say the angle. It's not exactly the angle, it's a wave vector, but you can see the angle and the position and according to the wavelength. So this is the dispersion I show you. So the data in red are the experimental data. No, the theoretical data, sorry. And the black one is the measure. So here, what you have is that if you just take the gold layer with nothing on the top, so you can measure the dispersion. So you can identify your plasma by the absorption. And when you deposit a thin layer of titanium dioxide of 1 nanometer, so it's very, very, very small, but you have a shift of this resonance. So this shift, if you take here, you can take the first point, for example. Here you were around 1.10, and now you are around 1.12. So you have a very small shift, but you can measure it. And according to the shift, you can deduce the amount of material you put onto your gold surface. So it's very sensitive. And if you increase more, you have 4 nanometers here. You see that the shift is increased. So this is one way to show you that this surface, this gold surface, the plasmon onto a gold surface is very sensitive to the local environment. You can have the same if you take a nanoparticle. It's a bit different. Here I just show you some theoretical data because I did it completely like this. If you take a gold nanoparticle of radius 50 nanometers and you change the local index, so around it, you put an index like R at the beginning, so it's in red, you have the spectrum here, so local equation. And when you change a little bit the index outside, how much you can change this resonance. So here you see that a modification of around 6%, not very strong, you see that the resonance is shifting. You can measure it. So here in this slide, you have the two examples of how we can use the sensitivity of the surface plasma, either a nanoparticle or either a surface, to use it for local probing. An example of a real application, it's a sensor which you can buy commercial now. It's based on the surface. So this is the principle. You have a prism like this. You have a flat gold surface. And you shine this surface with a light source, for example. You fix the wavelength and the angle. You put it a little broad in order to excite a few angles. One of these angles, it's in black here, is absorbed. So you see in detection, you see the black spot. The rest of the light is reflected. There is no plasma. So this position of this black position is due to the angle of the surface plasma. So you see a black because it's absorbing. And now imagine you put a cell, a flow cell of molecules you want to probe. And these cells will, for example, be linked to the surface due to beacon to have some exchange. And when it's linked to the surface, the local index will be checked. And you see that the absorbance, the position of this resonance will change. So this is how sensors, commercial sensors are based and are using today. So today, the goal is to show you a new kind of sensor, let's say, which is based on this kind of very well beautiful nanoparticles, which are called nano-bipyramids. Here you have an example of the size. Typically, the long size is between 80 and 100 nanometer, and the size, the lateral size is 20 to 30 nanometers. So let's go and explain you what are these called bipyramids, or why they are very interesting. So the first thing, so I'm not a chemist, so let's try to reflect about all questions about the synthesis. But roughly, here are some basic properties. So by changing the amounts of seeds and reactant you have inside the solution, you can make a growth from very small nano objects. Here you have the scale to very well shaped bipyramids, and you increase the size with the control of all reactions. What is interesting is that if you look here on the left, it's spectroscopic analysis in solution. So you have here the absorption of all this solution as function of the quantity of I think. So depending on this concentration, you can achieve more or less bigger particle, more or less anisotropic. And you can control the absorbance from the near infrared up to the visible. In generally, you don't go below too much 600 nanometer, and you can go up to in the near infrared. So this is quite interesting because you just have to change the size of the bipyramids, and you can have a very controlled resonance wavelength and absorption. This is very interesting for many applications. In terms of optical properties, that's what we're interested in. If you take here some calculations, you have here the shape of the bipyramids. It's set inside the air just to understand what is working. We shine it with the light. You have here the direction, which is K, and the electric field of the light will excite the electron from the left to the right. Okay, here I show you what is happening at the resonance. So I just come back here. For example, if you take the solution at this one, as a one-to-one, you have a resonance at this position. And when you excite at the exact position of this resonance, you have absorption. And the light here is located at the tip. So this is why it's very interesting, because you have a quite sharp tip, and you can increase the light at this tip. Here you have here it's on the field, not in the intensity. So if you want in the intensity, you have to put this value to the square. but you can increase the field here of more than 100 around it. Just to compare, if you take just a single gold nanoparticle and you shine it the same way at the resonance, you can only achieve a factor of 5 of concentration of the light. So here you earn a factor of 25 in the absorption and the location of this light. So this is very interesting if you want to make any interaction. For example, you want to put a molecule here and you increase a lot the interaction with the molecule. You set it at the tip, and it's quite interesting. So now I move on to one applications. What is about sensing applications. This has been done the PhD of Mike Rye. Here you have an example. I show you just an example from the sensors application, where they took these kind of bipyramids and they put some glucose inside. And you see that depending on the concentration of the glucose, you change completely the color. So the goal is to relate this change to the concentration or to the modification of the surround. Here is another example from the literature. Generally, what we define is what we call a merit factor, which is here, the M factor, which is how much the wavelength of the resonance is changing with the local index. So it's nanometer per refractive index unit. So the highest this value is, the more sensitive you are. So many objects have been tested in the literature. You have here a lot of examples. I will just focus onto the nanosphere, the first one. So you have a sensitivity which is around 44. And if you take the bipyramids, here you have a sensitivity of 500, more than 500. The problem with this kind of analysis is generally this is done in solution. Just as I showed you, I will just come back here on this slide. It's general thing in solution. So you lose a lack of the local specificity, and this is quite, let's say, sad. And for the understanding, it's a bit problem. You make a very average in statistics, no problem. This is a work, no problem with it. But we are really interested in what is happening at the single nanoparticle. So, okay, I will show you what kind of experiments we are doing. So this is an example. It's called spatial modulation spectroscopy, or SMS, just to explain you what is working. So we use a white light here. We focus with an objective or microscope on the single nanoparticle, and we collect the light concentration. So after that, we put it inside what we call the locking amplifier. It's not a problem if you don't understand. We see it before, but after, I will just explain how it's working. So the particle here is set onto a piezoelectric stage, so it can move outside the beam and inside the beam. So we'll show you with an animation how it's working. So the sample is moving, and you have the particle go outside and inside. So each time it does this, the signal of the transmission oscillates from a maximum when the particle is outside the beam. And when the particle is inside the beam, you have a minimum intensity because the light is absorbed. And what is interesting in this experiment is that here you have this manipulation of the transmitted power compared to the average. And this gives you what we call the extinction. For those not really aware, you can call it the absorption. It will be okay. So it gives you directly how much your particle absorbs. And the sensitivity is very important because you can, each time you have all the information. So I will just here briefly to explain again, but I will go more fast. What we are doing, the objective, the microscope objective focus like this. This is in green is the shape of the beam focused on the glass substrate. And here I show you the particle what is doing. So the particle will be moved inside the beam, but every time with oscillations. So the particle oscillates at this position, 2 point intensity each time. Yes. each time the particle is oscillating, and you get a signal. The signal is in red. It shows a maximum and after that. And in fact, why do we have this? It's because we remove the mathematical parts. But if you look at these two signals, so the shape of the light is exciting the sample and the signal recorded, you see that the two are the derivative of the other. So the image we are looking are in fact not the particle, because the particle is very smaller than the shape of light, but you have the derivative of the, and depending on the kind of modulation you do, here we try to oscillate with the frequency of f for the particle, but if you modulate at twice, you have the second derivative. So the image will, just to show you how the image will obtain, we will obtain a maximum of the signal in the center, and in this case, in the case of 2f, and one minimum on each side. So here is the results. So the sample are obtained like this. We take a glass substrate, glass cover slips, everyone uses. We do some chemical treatments, like mostly surface functionalization. We put some selenization on the substrate. And we make a drop of the gold bipyramid onto the substrate. So it would be sticked to the ligands, with the surfactants onto the selenization. So you have gold nano-bipyramids sticked near the surface. We can do many experiments. Here you have an example of an image obtained. So you see here you have the signal I showed you. So you have maximum on the lobes, right? And we can identify 6 here bipyramids. And the thing what is interesting is that if we put some, let's say, target onto the surface, I will not show you for clarity, like for example, a microscopic grid, you can locate where these particles are on the substrate. So for example, if you put them inside water, you can identify the same 6 here bipyramids. So with that, what we did. So first of all, we constructed a flow cell where we put the sample into a liquid. Why do we do this? Because we want to control the local index. So we put everything in water, for example, or glycerol, for example, for test. And on the left, you have the results for one bipyramid, the spectrum for one bipyramid. So here you have in red the result obtained for bipyramids set in air. So we don't put any water around. And when we include water, you have, so you see a shift of the source. So you have the value here. So we go from 730 to 787 nanometers for the resonance wavelength. And when we put now a mix of 2 for 1 of water and glycerol, with you have the index here, you can see also we are available. We can see the shift. It's very small here. It's only 7 nanometers, but you can see this. So so the idea is to quantify this for single bipyramids, as we said, but also to see if the technique can be reproducible. This is really important. So what we did is the first thing we set at the 6 bipyramids, we identify the resonance, and we see that depending on the index, optical index, you can see that you have an evolution of the resonance of the plasmonics. With this, we can extract the sensitivity. It's around 200, a little less, for this specific sample. What is interesting also is that you can say, okay, if I want to use this as a sensor, can I go back? I mean, once you did the experiments on the glycerol at the end, can you go back to the air? So the result is the following. So we set the same 6 bipyramids, but we rinse, we clean the sample, we go back in air. So here you have the first result, and you are here. The resonance is increasing with water and plus glycerin. And when you go back to air, you see that there is a little shift, but it's coming nearly the same as it was at the beginning. The other thing you can ask is about the edging, because the problem, if you want to make a sensor, you want to use it many times during the month. So here we did the same, we took exactly the same sample after 8 months in air. And you see that the resonance is not shifting too much. The final thing is just to prove that we are doing exactly the thing on the 6 same bipyramids. You can probe it with the image, but you can do also some SEM imaging. So here you have the shape of the bipyramid after many cycles of water and glycerin and after 8 months. So you see that the 6 bipyramids are still looking quite okay after 8 months. So this is this was the first step of this work. And now the goal is to go more to detect, for example, ions, very hard ions, for example, polluant inside water and this kind of stuff. So this is was the first part of my talk. The second one, I will go more fast because I'm not sure it will interest you, but I can just explain. This is a PhD of Miss Wu from Vietnam. And the goal is to use this bipyramid for applications. So I will just explain what we are doing. The setup is a bit different. The goal here is to measure not the absorption of the light, but the scattering. The technique may be, it's a bit similar to fluorescent spectroscopy if you want, but not completely. Let me explain. You shine the sample from the left to the right. You shine it with the first objective with very small angles. It's in gray. So the light is going through the second objective. It's going through, and after that, you can enter the imaging, for example, on the right. Now, what we call dark field imaging is you put a blocker to stop this direct light. And the thing is, what is interesting is that if you have a nanoparticle on the substrate, it will scatter the light at other angles. It's what I put here in red, and you have the scattering, which will be in different angles. And this scattering will not be stopped by your blocker. So the light is going outside, and you can make an image. You have an example in figure C. You have only bright spot in a dark, very dark background. And on the signal to noise background can be really high and very, very interesting. And if you now take one object like this and you make a spectrum, and you have the spectrum here of the single gold bipyramids. So with this kind of technique, we can also analyze bipyramids. You don't need anything. So we'll skip a bit the thing. What is interesting is that with this technique, we can measure the polarization of the light. And with this, with a bit mathematics and to analyze the data, you can have the orientation of the bipyramid deposited on the glass. So what the problem is the following. The bipyramids, they are surrounded by ligands. And these ligands, in fact, it's CTEB. And CTEB, when you deposit the bipyramids on the glass substrate, due to this, you have interaction with the ligands on the surface, and you can have two main orientation of the bipyramid I show here in these two schemes. So it's very important for us to know the orientation. So with polarization, we can achieve here a very interesting analysis and show that these two orientation are possible. And our technique is working for anything that scatter light and also can be applied for fluorescence. I did it for fluorescence molecules, for example. It's the same idea. And so what we are interested in fact, in the case of the photonics, it can be very useful also for sensing, is that if you deposit these bipyramids near a cold film, you can have a strong interaction with light in between the two. And one of the interesting things, it's the thing my PhD with who is working on, is to use these bipyramids to convert, in fact, the light you excite from the top inside a surface plasmon, so along the gold field, to propagate the light inside this, which can be very interesting for photonic applications and to control where the light is going. So I will be skip just one image to show you what we can observe. So here you have an example. If you shine the sample with a white lamp, so you shine with a big spot, you can observe in the direct image, not a dark field. If you look in with your eyes directly, you can see some black spot here. It's due to the absorption of the bipyramids. And if you put it in with you set now the blocker, as I show you, you have this dark field image. So you can really identify. You see here the two differences between the images: left without blocker, and right with a blocker. We'll skip a bit because it's a bit complex for you. What is interesting is this one. It's my last slide. It is how you can achieve this conversion of the light. So here on the first image, you have a white lamp excitation. So you said it was white light. So you observe that you have two bipyramids here. It's just in scattering. You see two bipyramids. They are separated for a little size, 7 micron. And now I can use some laser and to excite these two bipyramids. And what you can see is when I excite these two bipyramids, you have the scale, it's 10 micron. But you see that the light is scattered in all directions, but the scatter is not located around each bipyramid. You see that the light is propagating everywhere. And if you set, for example, a polarizer, you can force the light to go, for example, either vertically or horizontally. What is interesting is that you see that in between the two bipyramids on the last right image, you see that there are some fringes of interference. So this means that the two bipyramids are talking to each other. So you can see what is interesting. The interesting of this is that if you want, for example, to achieve, you can call it Fret Forster resonance transfer, for example, of a molecule to a donor to an acceptor. But with this kind of photonic device, you can achieve, I will say, a higher distance. You can increase the distance of excitation between a donor and an acceptor. You can increase it here about around a few 10 micron. So you can increase by, I think, something like 1,000. You can increase the interaction distance. So this can very interesting for any applications. So this is my conclusion. So I